kinetics is basically the objective of dynamics of rigid bodies, no? Because kinetics deals with forces. No? Unlike kinematics, we don't care about forces as long as we only wow, kinematics only discuss geometry of motion such as acceleration, velocity, and its displacement. No? However, in kinetics, uh, we still use kinematics because we are dealing with uh, theory like Newton's second law, in which deals with forces, but according to Newton's second law, mass, the force is equals to mass times acceleration. And we have already finished discussing that last week, no? So this, I think I have given you assignment, so I suppose you submitted them already. No, I haven't checked it. Okay. This morning we will discuss. Still, we are in kinetics of rigid body, but different way, different approach of solving it. No? Just like using energy methods, energy like conservation of energy, something like that. No? Aside from Newton's second law, we can still solve problems in dynamics using energy and work methods, no? Work and energy methods. So that involves law conservation of energy. So it's like that, no? So uh, and also I have mentioned this earlier that I have posted lecture materials in kinetics, no? In kinetics in the e-learn. So that material is very good. It consisted of maybe more than 10 problems, solved problems with explanation how you do it. Okay, and in fact, I am going to discuss one of the problems there, no, that involves kinetics of rigid body. Okay, so I will before I will start the lecture. I think I'm going to present that material, lecture material that I have mentioned. Okay, so uh, the picture material is I think here. Okay, where is it? Okay, here. So I hope na makita ninyo ni sa inyong kuano. So nag-load na sa inyong screen.
Yes, sir.
Nana. So actually this is I take this from the website, no. In fact, this is just P6 4A, no, in other courses, no. I think this is one of the subject in one of the university in uh, United States or maybe Europe, no. So P6 4A meaning this is the fourth subjects of P6. So and maybe their P6 4A is about dynamics of rigid bodies, no. So well, dynamics of rigid body is also the fourth one. No? You have P6 1, you have P6 2, and P6 3. I think that is statics of rigid bodies, and P6 4 is about dynamics of rigid bodies. So, but in our case, we call it dynamics of rigid body. We do not call it anymore P6. Okay. So anyway, you have some theories here. You have some notes, very important notes. Okay, there are guides on how to solve them. Okay, and its applications there. Okay, so everything's there. Sorry. So and then we have question and example problems. No, uh, so like this. So there is even a handwritten solution. So maybe from one of the students of the author. Okay, and there is so a lot of problem, and then there is somewhat guide, no, a guide on how you do it. Even the formula is given there, and there's also discussion, no, very straightforward discussion. Okay, so naisa sumusunod. Okay, so we will continue. We will continue. Okay. So there are a lot of problems really, no? And outline on how to solve them. So it's being explained, no? So well, it's really one group. Just like this one, no? This is just very simple. This is just converting RPM into angular acceleration. So an elliptic fan goes from rest to 1,800 RPM in 4 seconds. So from 0 to 1,800 revolution per minute in 4 seconds. What is the angular acceleration? So it's just a matter of converting uh, units, no, into RPM to radian per minute. No? So a radian per, not, acceleration is different. No? This one is RPM in 4 seconds. That is already an acceleration. If you divide 1,800 RPM by second, so you will have an acceleration, but the unit is not the one that is being used here. The answer, because this in terms of angular acceleration, so your unit should be in radian per second squared. So third solution. Okay, we have also I think DVD. Yeah. So buhatan na ng program sa yan circuitry. How the DVD turns, no? That's an RPM. So the RPM so steadily increase after 1 minute. It stops. It becomes the RPM is steady up to 4 minutes per seconds, and then slows down. Okay. So we have already discussed things like this in the beginning. No? This is basically kinematics. No? So we are done with this. Okay, what is the rotational kinetic energy of the Earth? This is interesting because it talks about Earth. Okay, assume that the Earth is a uniform sphere, but this is a very rough assumption. The Earth is not uniform sphere. Data for the Earth can be found inside the back cover of the book, and this is not a book, like that. But anyway, it's being solved here. So you have rotational kinetic energy equals to 1/2 moment of inertia of the Earth, which is a sphere, and multiplied by angular acceleration, the square of angular acceleration or angular velocity. Okay, so dako kayo 2.57 times 10 to 29 joules. No joules. So something like that, no. So the problems involved given here have solution already, and then there's also an explanation, and there's also a formula, no, a formula. So this is a good. So there are a lot of problems here, both in kinematics and kinetics, no. So okay, so the problem that I am okay. This one is, I think, is already kinetics, no, because it involves Newton already, no. So like this, no. But this one, I think it's just fine. Looking for a 20 centimeter diameter disc in the figure. Yeah, this one. Can rotate on an axle to its center. What is the net torque about the axle? So the forces are given. This one creates moment about the center. No? All you have to do is just to sum up the moment so about the center. No? So there are four courses actually, and all of them rotates, and yeah, at least one one course is not included because it has a line of action that will pass through the center. Basically, there are only three courses. Now, two of them are B and C rotates tend to rotate about the center of the disk in counterclockwise manner, while A rotates in clockwise manner. Okay, so basically there are only three, okay, and then you have negative 9.94 Newton meter. Okay, so negative means that it is a clockwise rotation because the first thing you will do is to make your own convention, no? Whether counterclockwise is positive or clockwise is negative, like that. No? But this is not the problem I'm going to discuss this morning. No? I'm just giving you a tour on what is this material, teacher material all about. Okay, then small. Okay, so we will continue. So this one is also another problem. No? So I will just skip with that now. Okay. So this one is also a very interesting problem. You have a 5 kilogram cat and a 2 kilogram bowl of fish. Okay. So the other cat is 4 kilo on the other side. Okay. How far to the left of the pivot point must a 4 kilogram cat stand to keep the seesaw balance? Okay. Tingnan na. So, sa nila nga magpagsubag o balance. But I think cat cannot do this, no? Because I don't know if you can. Well, okay. This is problem about cat, but uh, to be solved by humans, no humans. Okay. A 5 kilogram cat and a 2 kilogram bowl of fish are at opposite ends of the 4 meter long seesaw of the figure below. But the seesaw has its fulcrum on the middle of the 4 meter long seesaw. Seesaw. How far to the left of the pivot point must a 4 kilogram stand to keep the seesaw balanced? Uh-huh. Balance. How far? Okay. So, ang 5 kilogram cut to us sa other end. To us sa other end. Now, ang pangutana is how far? No? So, gibutang na siya siguro 2 Malaysia. So, okay. So, this is just making it balance. No? So, 1.5 din siya. Okay. Motion 6 times 2. Okay. So, anyway, this is not our problem. It's a problem of the cat. No? We will not solve that. Okay. Okay. Uh, this one is also similar to the problem that I'm going to solve now. It's about a solid sphere that is placed at a height of 30 centimeter on a 15 degrees slope. No? So, gibuhian siya. So, murowid siya after. Okay, it is released and rolls without slipping to the bottom. From what height should circular hoop over juice are be released on the same slope in order to equal the square speed at the bottom? So actually, Duhan is a case, no, but I will discuss this later. No? So the problem that I will be solving is this one. Okay, this one. This is the problem that I will be solving this morning. Okay. Okay. I am interested in this problem because it talks about conservation of energy. No, conservation of energy. So remember that I mentioned that we will be solving problems about kinetics using energy and work method. Okay. So this problem is a typical problem that can be solved using work and energy methods. Okay. So it's really very simple. It's easy to understand. No. So you have a sphere that flows at 5 meter per second. No. Let's say starting from here. No. Here. So it rolls steadily. No. Meaning no acceleration because constant speed man. 5 meter per second to the right. No, when it reaches the point where the incline starts, still running at 5 meter per second. No, now because it goes up, no, it goes up. So the velocity of the sphere, or the speed, the velocity of the sphere as it goes up, it slows down until it stops. Okay, meaning it reaches already its highest point. Just like throwing a stone vertically up, you give it an initial velocity, and that initial velocity is countered by the gravitational attraction. So the stone that you threw vertically up will slow down until it stops, no? And the point where it stops is what we call the highest point reached. Okay, and then once the highest point is reached, the stone will fall back to the point where it started. No, so starting with a slow velocity, and then finally it gain its speed or velocity as it goes down, and then back to the point where it was. Okay. This problem is uh, the hollow sphere, no? Hollow sphere may giingon din eh. So this is something we mo kuha niya no gi describe niya unsa gid ang sphere. This has something to do with moment of inertia, no? Because if you have a hollow sphere, the moment of inertia is different from the moment of inertia of a solid sphere. Okay? So mo na di ang the importance of describing properly the the shape of a sphere. No, no, not the shape, but the description of a sphere. Okay. So, bali, when it reaches the bottom of the incline, it has an initial speed of 5 meter per second. So, as it goes up, it is countered by gravity. So, the hollow sphere tends to slow down until it finally stops. I think the problem is how far does it roll before reversing its direction. So, before it reverses its direction, the velocity is set to zero, or shall we say, the hollow sphere stops rolling. Okay, that is the point, the farthest point that the hollow sphere have reached, because at that point, after that, it will reverse its velocity. No, okay, so the problem is there. Okay, uh, the okay, so our model is something like this. No? So I will solve it here now. So uh, I will present another one. So I will stop sharing that one, and I will present another window. This is our lecture for this morning. Okay. Okay. So this is it. No. So we have here yeah, kinetics of rigid bodies. We will put it work and energy methods. Work and energy methods. Okay. So we have a hollow sphere. It's rolling along a horizontal floor at 5 meters per second when it comes to a 30-degree incline. So as you see in the video, this is a 30-degree incline. How far up the incline does it roll before reversing direction? So we are looking for S. No, S. Okay. So this is our model. No? So our model is, we assume that the hollow sphere is a rigid rolling body and that the sphere rolls up. No, wala din is rolls up the incline without slipping. Okay. We also assume that the coefficient of rolling friction is zero, so there is no friction involved. Okay. So we will just uh, our solution looks like this. No? So this is our solution. So the the solution is that so we call this how did we call this? Okay. So the solution here, solution. Okay. The initial kinetic energy, which is which is the combination, no, the combination, which is the combination of rotational energy, 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 and translational, translational and translational energy and translational energy is, is is transformed is transformed into gravitational gravity gravitational and potential energy. Maganda siya. So how many types of energy? Okay, so if they are spinning translational or gravitational and potential energy. Okay. So from that worded solution, we will make an equation. Okay, so the equation of that is uh, equal to this, no? So bali we have sa tawag ani PIUDI PIUDI so PI plus U Di is equal to Pf, the potential, the rotational energy plus UGF. UGF. Okay. So all of this is initial, I think. Subscript, potential energy. The work done, and then we have the final potential energy, and then the work done by the gravity. Okay, by the gravity. So this is the equation. So take all this conservation of energy equation. Okay, is it? No? So where TGI, where TGI is the initial. So TI is the potential energy, no, kinetic energy kay Kiman is the kinetic energy, energy at bottom, at lowest, at lowest point in the incline. So the equation of this is uh, ato sa konon at the lowest point, ato sa i-define tanan. Okay? Before we set up the equation. And then PF is basically the final, no? The final, oops, PF at highest point, highest point, highest, high, or farthest point, highest point. Okay? So, the kinetic energy at highest point can transform into a potential energy. And UGI is the translational energy, no? Translational energy or the work is the translational energy. So the rigid body, the rigid body, or the hollow sphere, and UGF, atau sering subscript. UGF is the UGF is the gravitational gravitational potential energy of it. Potential energy of the hollow sphere. Hollow sphere. Okay. So period. Now we have an equation. So kinetic energy at the lowest point is Vi is equals to one half, no, one half in V I squared, no, in V I squared. So this I is a subscript and this one is square. Okay, Ki here. Okay, so solving this one, actually, actually Vi is equals to 5.0 meter per second. So that's the Di. The square of that is 25 divided by 2 is you will have uh, divided by 2, your Ki becomes 25. So you will have the mass. What is the mass of the sphere? Okay, there is no mass. We'll just let it as m. Anyway, it is constant. Then Bi of 5, square of 5 is 25 divided by 2. So this is equal to 12.5 m. Now, the unit here is just the meter squared per second squared. That's the, we'll just put the unit in a parenthesis, no? Meter squared per second squared para hindi siya makasagol. That's the unit. That's it. That's it. Okay. Now, TF is 0 meter per second. Why? Because the at highest point is equal to 0. This is 0. Just say 0. Because the V of the high at the highest point is 0 because as the hollow sphere moves up, its speed is slowing down until it rolls up no more, no potential to 0. So of the 4 equation here in our formula, we have already did that too. So next we are going to solve the UGI, no UGI. Pinasan, the UGI. So UGI, UGI is equals to weight. So referring to our figure, is basically equals to the weight potential energy, no? The weight times S, no? Times S. Okay. The weight times S. So I'll just, but it's not S, but it's the direction with the same direction as the weight. The weight is vertical, that's mass times gravity, and so you're not using S, but you're using S times sine of 30 degrees, or basically y1 minus 0. No? So that's the equation here. So mass times gravity, that's the weight of that is the weight of the hollow sphere, then multiplied by the vertical distance because the work done should be weight, the force times distance, no, in the direction of the force. Okay, so the distance, we are not going to use s here, but y1. Okay, so we just say that's y1, y sub 1 in the figure, or that is equal to let me see y subscript is here. Subscript ba? Oh yeah, that's subscript. But it can be converted into S because that can be converted into MJ times S. So that's the S. So where S is the is the distance from distance the this distance traveled to go doubled by the rigid body. Okay. So sa upat equation, isa na lang, no? That's the that's the potential energy. This is kg. Sabi, sa taas na ito ha, kung formula is UGI. UGI is equal to that. MGYO din siya. MGYO. 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 Okay, at initial man. YO. So UGI is 0. I just want to say UGI is 0. Yeah, 0. This is 0. 0. 0. So, saan eh? That's me. Lahat pa ni siya plus di ay. The, the kinetic energy, initial, the kinetic energy is d squared plus 1/2 I WO squared plus 1/2 I CM as the center of mass, omega squared, omega I squared. This I is subscript, and this is CM is also a subscript. Okay. So, mauna siya 1/2 MDO. Okay. Okay. So, uh, this is plus one half, one half. CM is equals to two-third m, two-third m times the radius times this one. Okay, that's it. Kf is 0. So Kf is not entirely 0. Okay. So Kf is actually I will spill this out. No? That is equal to that. But the velocity there is final. We are talking about final velocity. Okay, but final velocity is 0, and also this is final. Final angular acceleration should be 0. So basically this is 0. So because b at the highest, 0. So that is 0. So we have UGI. So next is UGF. So UGF, copy. UGF, yeah, copy. So for UGF, and this one is F. So this one is Y1. Okay. So UGF is Y1. UGF. UGF is Y1. Y1 is, we will solve for Y1. No? So you just see it like that. Okay. So repeating this, repeating that, knowing that that is our equation. Okay. So we have GI equals to 12.5 m. Okay. So mauna siya. So PI is basically equal to 12.5 m plus 1/2 times 2/3 is equal to 1/3. 1/3. Then you have mass. Actually, when we talk about velocity, uh, velocity is equal to, I think, omega, no? Omega R. Omega R or W divided by R. Okay? Or they have WR, angular velocity times radius, no? Angular velocity multiplied by R. When you talk about B squared, B squared, okay, B squared, that is equal to W squared R squared, okay? So in other words, also we can memorize, R squared in daan, R squared. So this one is R squared and R squared. R squared. Okay. So B squared is basically W squared R squared. Okay. So if that is the case, that B squared is WR squared, so this one can be converted into VI squared. VI squared. So that's it. Oh, VI squared. This one is wrong. Okay. So that's the key I here. Then our equation requires UGI, so nano siya plus. Nano siya plus diha. Plus UGI. UGI is 0. Is equal to EF is also 0. 0. Then we have plus UGF. UGF is in GY1. In GY1. Okay. So you have this equation. Okay. So knowing that, actually BI is 5 meter per second. That's the initial. So that's 25 divided by 3 plus 12.5. So it becomes 20.8333. M will cancel. This equals to J times Y1. Okay. But okay, that's it. This one should be 16 instance. Okay. But S is equal to but Y1 is equals to S cosine 30. S cosine 30. So we will we will uh we will change this into this one. Okay. So this one is not Y1 anymore, but this one is. We'll change this one by 9.81. That is application 9.81 times S cosine of 30. No, sine of 30. Sine of 30. Because it's vertical. Sine of 30. And sine of 30 is 0.5. No, S times 0.5. So this one is equals to S times 0.5. Sine of 30 degrees is 0 degrees. So S there be solved, no? 20.83 divided by 9.51 times 2. So 4.243736 meter per second. That's the answer. This is the answer. Okay. So 4.3. So you might wonder what is ICM. From the formula of the moment of inertia for the hollow sphere, that is equals to 2/3 mr squared times angular velocity of at I. No? So these are the potential and the transitional and the rotational moment of inertia. Okay. So we satisfy the equation of conservation of energy so that we can solve for S. So this is the answer. No? This is the answer. Okay, so I will upload our discussion this morning. But before I will dismiss you. I will give you an assignment. No, an assignment. Okay, so this problem actually, but I'll change the data. The data. Okay, I'll change the data. So for the meantime, I'll take a break. Huh? I'll take a break. Okay, so I will take a break. So if you have some question, I will come back. 5 minutes.